All right. Do you hear me? Can you write something in your Discord if you can hear me? Great. All right. Uh, so what we learned last time is there is a so-called moments of inertia. The moments of inertia is as important as the mass in the translation. Oh, I see. Just a minute. All right. Yes, I see. I only checked the Discord, but we'll open it to see both. Alright, so moment of inertia is something that can describe not only the mass of the system, mass of the body, but also the shape of the body. How can we use it? If, for example, we have a cylinder and rotate along this z-axis, the moment of inertia is 1 over 2 mr square. We can calculate easily the rotational kinetic energy, just 1 over 2 moments of inertia times omega square. The form is very similar to the translational kinetic energy, that 1 over 2 mv square, but in this case we have to calculate also with the shape of the body. This is what we did last time. In some case there are independent parameters like the L, the length of the cylinder right now. We can calculate rotational kinetic energy for any of the body when the moments of inertia is known, and I gave you some example. I will check how you solved it. What is torque? When a force is exerted on a rigid object, the object starts to rotate if the so-called line of action does not go through the rotational axis. That means if we try to rotate here something and the force goes like this, there is a so-called level arm. This dashed line is the line of action, so technically you just extend the vector of the force in any of the direction and measure the perpendicular distance between this line of action and the rotation axis, and this is the level arm. If the level arm is non-zero, this torque is a non-zero number. That means the body tends to rotate around that axis. In this case, the rotational axis is easy because it's here, but if there is a so-called free body, the rotational axis should go through the center of mass of the body. But let's go back later. So I suppose you still remember what is this vectorial multiplication. If the motion, so the force and the motion is in one plane, like on the plane of your screen, this will be F times D, this will be F times the distance between the force and the axis times sinus phi, which is the phi between the R and the F. How can we use it? So for example, just go back again to the translation, the F equal m times A. We have similar Newton's second law for rotation. The torque is the body, the torque is the force, the torque is the source of the acceleration, but in this case, like the force for translational motion, if the torque is non-zero, and if we know not only the mass, but also the shape, technically the moments of inertia of the body, we can calculate what will be caused by this torque, what will be the angular acceleration. If there are more force on the body, if there are more force on the body, the net sum of the torque will be the net torque. The sum of the torque will be the net torque that will cause the acceleration by only divide it with the moments of inertia. If the axis is fixed, we will use it several times. We only have to calculate this net torque to get the angular acceleration. Let's see some easy example. For example, this is the seesaw. I think you saw such an example or not. You have any experiences how it works. So let's suppose this is a massless seesaw with two bodies at different distance from the rotational axis. The condition for balance is the net torque has to be 0. The net torque, since this motion is again on the plane of your screen, the net torque we can calculate the torque from the net torque from the force 1 R1. This is R1 cross F1. You see, this is, if this is R1, this is F1. You can play with your right hand. The torque will point towards the U, so from the skin to your face. If you calculate the other torque only using your fingers, this will point from your face into the screen, so the direction is opposite. So since there is no way to move anywhere else, only on the plane of your screen, technically this vectorial sum can be written as two scalars. So let's choose an opposite direction. Opposite direction is towards the U. In this case, torque 1 is positive, torque 2 is negative, and therefore torque 1 equal torque 2 is the condition for the balance. So this is a scalar F times D, the level arm. In this case, if you extend, if you create the line of action, just drawing a line through the vector of the force, the level arm will be exactly the length of the R1, and the other level arm will be the length of the R2. So therefore, let's use some number. So if, for example, this is 2 meter and 10 kilogram, that's 20. If this is, wow, I forget to, yes, it's 2 meter and 10 kilogram, this is 20 Newton meter. If the force, it's 10 kilogram is 100 Newton, 100 times 200, 100 times 2 is 200, so the torque 1 is 200 Newton meter. If this is 15 kilogram, which is 150 Newton, the R should be something that if you multiply it with 150, you have to get 20. So that's 0.6666 meter. Oh no, upside down, 1.3333. I found a nice example, the ladder example. If you have time, just check it. In this case, we have to, how can I say, think differently, because this ladder example, sorry, in the YouTube I can't open any other YouTube channel because the YouTube will delete, in this case, my channel. But if you open it, and you can see how can we calculate ladder example, and in this case the so-called free body assumption is very important. So free body means there is no fixed axis, and we will use the condition that if the body is free, even it's a ladder on the wall, but if we can move the abstraction to the free body, the body has to rotate around its center of mass, and that can help us to solve the example. Inner forces, if we have a axis of the rotation O, and if there are two particles, and let's assume there is an electrical or gravitational force between these two, we can calculate the force, the torque will be, the sum of the torque will be 0, so therefore the net torque, the sum of the inner torque, has to be always 0, and that comes from the Newton's second law, the force anti-force. That means if there are inner forces, like there are inner forces anywhere, so in your table, and the table won't start to rotate because of these inner forces. So we always need some external force to rotate a body. What external force can we imagine? So there's a cylinder that can rotate around this axis. The radius is r. The mass of the cylinder is m. You can calculate the moments of inertia, and this external force is, for example, force comes from this box. This box has a weight, and there is a T force. This is just a parameter, but we know if we have a string, and if this is not a spring, this force has to be the same at the box and at the cylinder. So right now T is nothing else, just a parameter. How can we describe the motion of the box and the rotation of the cylinder? The rotation of the cylinder is, the torque has to be equal the moments of inertia times angular acceleration, the torque, in this case, this T force, and since the level r is the r, it's T times r. Therefore, the angular acceleration is T times r, this is the torque, divided by the moments of inertia. What is the net force on this box? The net force is the weight minus this T. That has to be equal to m times a. So on the left there is the net force, and this is only Newton's second law, net force equal m times a. Therefore the a is weight minus T divided by m. If this is a pure rolling, so no slipping, no breaking on the strings and so on, the v, the velocity, has to be equal to omega times r. I have to change it to capital R. Just I create a memo. And also, if this is a pure rolling, pure rotation, the acceleration is connected with the angular acceleration via r. So if we move with this a is this one, alpha is this one, it's connected by r, and therefore this force appears to slow down the mass and rotate up the cylinder is mg1 plus mr square I. On the seminar, we will solve an example with normal numbers. Alright, let's go back to work. You know, work is energy transfer. The net work done by a body that can rotate is and can't translate, for example, is the changes of the rotational kinetic energy. So if you can measure the omega at the beginning and omega at the end of the force, of the x of the force, you can calculate what is the work done by that force. In some cases, if the body can rotate and translate, of course, the net work done by this external force is the sum of the translational and kinetic energies. That will be used for the pure rolling. Pure rolling is a rolling without any slips on the horizontal surface. So you can imagine like the wheels of the cars, normal case, behave like a pure rolling. But for that, for rolling, we will need the friction, because this is the torque that rotates, for example, the wheel, the friction between the wheel and the road. But in this case, what we learned last time, that if there is friction, we can lose something. I can find, yes, here. You remember? So if there is a translation and we have friction, we lose some work, because some part of the work will be transferred into internal energy, will be transferred to heat, and not only for kinetic energy. But in this case, that's kinetic friction, but the pure rolling of a wheel, this is static friction. That means there is the surface of the wheel, so the touching surface of the wheel and the road, that does not move, and therefore the friction can't create any heat. This is ideal work, of course, if you check your wheels, even your bicycle or car, after driving or riding a lot, it's warm. But in ideal case, this friction for pure rolling won't need any energy. So in this case, the work can be transferred into kinetic, translational and rotational kinetic energies. One example for pure rolling, if the cylinder rolling without slipping on an incline, the potential energy will be transferred to translational. There is a speed of the center of the mass. The 1/2 mv square is valid here, so there is a translational kinetic energy, and since it rotates, there will be a rotational kinetic energy. We will solve it on the seminar. The other example we will go through is the pure rolling, when we push or pull a body with the force that goes through the axis of the rotation. So this is a free body. If the axis of the rotation is the center of the body, if one force goes through the center of the body, the axis of the rotation, that won't create any torque. It's only the friction can create torque that rotates the body. That's a nice example, and there are several ways to solve it. If the friction is not enough for pure rolling, that's a tricky situation, because in this case the velocity and angular velocity is not connected by the R, but we have another 2 seminars to practice it. And if we know the acceleration, angular acceleration, back to the kinematics, by integrating the acceleration and angular acceleration, we can have the velocity and the angular velocity. By integrating again, we can have the displacement and the angular displacement. And that's true for pure and non-pure rolling. So I hope you have enough time to practice it. So this is a nice example. I can show you studied you've understood everything. And right now I have an extra course from 9, so if you are still free, check this example here. But for that, of course, I have to send you my presentation to click on it. Just a minute. Yes, it's here. I sent it in your Discord, or I also send it to the YouTube chat. So that's for all for now. That's all for now. So right from here we have only a few things we have to talk on the lectures. So the most important is to be able to calculate these example, to solve these example on the seminars. So any question for informatics students, and parallel with that I can answer some any other questions. Just a minute, I stop the streaming and will be available on Discord. 1 second.